Hello, Assalamualaikum warahmatullahi wabarakatuh. My name is Nordana Najamitin Muklis. My metric number is DN220026. So today I will sharing you about introduction and application in mechanical motion. So for the introduction, the free oscillation and phenomena observed in various systems involve periodic motion without external influence once the system is set in motion. For the example, free oscillation refer to the rheumatic back and forth motion initiated by an initial displacement. The behavior of free oscillation can be described mathematically, highlighting the system inherent dynamic. So the Beyond's pendulum free oscillation is a fundamental concept found in reserved physical system, showcasing the innate ability of certain structures to oscillate autonomously. So the next slide is application. As a car goes over a bump, the spring in its shock absorber assembly is compressed, but the elastic potential energy of the spring immediately forces it back to a position of equilibrium, thus ensuring that the bump is not flat throughout the entire vehicle. Spring alone would make a bounce, right? Hence, a modern vehicle also has shock absorber. The shock absorber, a cylinder in which is a piston pushes down on a quantity of oil, act as a damper that is an inhibitor of the spring oscillation. Most oscillation particles are subject to damping or the dissipation of energy primarily because of the friction.
Assalamualaikum warahmatullahi taala wabarakatuh. My name is Muhammad Haikal bin Muhammad Nazri, and now I will presenting the calculation part for this project. So the first question of this project is to find an equation for the position of the spring when it is under undamped free vibration. So for the first step is to find the weight by using the formula W equal to mg, and we will get the W is 49 Newton. And then after we get the value of weight, we need to find the spring constant, which is K, and we will get the value is which is 490 over 3. And using the birth value, we will need to find the undamped free vibration by using the equation and insert the value into the equation to find the value of m or beta. So by using the equation in the step 4, which we get the equation from the value that we find before, in we will use the equation for two different stations, which is x at the time of 0 is equal to 0.2, and x bar at the time of 0 is equal to negative 2.5. And we will get the value of a, which is 0.2, and the value of b is which is negative 0.438. So from the odd step before we used to get the each value for the equation, we will get the answer of 4 final equation, which is xt is equal to 0.2 cos square root of 850 divided by 5t minus 0.438 sines square root 550 divided by 5t. So it is the final answer for this question. So next, for the second question of the project 2 is to find how many cycle per minute will the system execute. So to find it, the answer is first step is to find the weight, which will use the formula of W equal to mg, and we will get the answer 960,400. So the second step is to find the spring constant K, which is we use the K equal to weight divided by the undamped free vibration, which is 1.09, and we will get the 8.811, which is the spring constant. And from the spring constant, we will insert it into the formula of time period of oscillation to find the second, which is the time, which we will get the 2.094 second. So next, after we find the time period value, we will find to the frequency, which is f, and how to find it is using the formula f equal to 1 over t, which the t is 2.094, and we will get the frequency value, which is 0.478 second. And after that, we will use the last step, the last formula, which is to find the number of oscillation per minute, which is 0.478 multiplied by 16, and we will get 28.7, or the exact value is 28. So the system execute 28 cycles per minute from the mean position. The ball is stretched to a distance of 0.16 meter.
A mechanical motion. Application refer to practical use of mechanism or system to achieve specific functions. This can include designing gear for smooth rotation, employing cams for controlled movement, or utilizing linkage to convert motion. These applications are crucial in various fields like manufacturing, robotics, and automotive engineering, enhancing efficiency and precision in mechanical systems. An example of application in mechanical motion is in the automotive industry, where a crankshaft mechanism converts the reciprocating motion of the engine pistons into rotational motion, ultimately driving the wheels of a vehicle. A common example of a mechanical motion in daily life is the door hinge. It utilizes a simple rotational motion, allowing the door to swing open or close smoothly. The hinge mechanism consists of interconnected parts, demonstrating the application of mechanical principle for practical function in something as routine as entering or exiting a room. You could say that application in mechanical motion play a fundamental role in various aspects of our daily life, from the hinge on the door to the intricate mechanism in automotive engines. These applications highlight the importance of understanding and utilizing mechanical principles to create efficient and functional systems.